Thank you for coming, everyone. I'm Jason Ansel, and I'm going to talk about Helion, which is a new high-level DSL for kernel authoring. So starting off with a motivation, Helion is a new DSL that sort of exists between the levels of abstraction of PyTorch and Triton. So it's lower level than PyTorch, higher level than Triton. And one of the big motivations we saw working on PyTorch and Torch Compile is a lot of users were asking for more control. They wanted to say exactly which operations got fused into a specific kernel. And for that, they were often switching to kernel authoring DSLs, but they didn't want to go as low level as something like Triton or CUDA, and instead wanted something a lot closer to the level of abstraction of PyTorch. So you could sort of think of Helion as PyTorch with tiles. It's sort of like a PyTorch 2 native way of authoring kernels. And then looking at it from the perspective of Triton, Helion automates a lot of stuff that is manual in Triton. So a Helion kernel should be less code than the equivalent Triton kernel. And Helion has a embedded autotuner in it. And the design of the language is tightly coupled to the design of the autotuner. So we took some inspiration from languages like Helion, which have a split scheduling language and semantics language. And so you could view sort of the Helion DSL as the semantics language, where we try to keep all the hardware details out of the language. And then there's this auto-tune configuration that specifies all the hardware details and how to map that computation to the actual hardware. And we generate these configurations using an auto-tuner. And you could view this autotuner as sort of a way to take a lot of the effort of optimizing kernels and shift it from the user to the machine. So you can replace human effort with autotuning time. So here's an example of what a matrix multiply looks like in Helion. In this kernel, you have basically two main sections. You have this outer section, which is just regular PyTorch code, which runs on the host. It allows you to allocate output tensors, do size computations, etc. And then you have this inner part, which is bounded by this hl.tile loop. And this gets mapped to the device. And within this hl.tile loop, you can use standard PyTorch operations, and they get automatically mapped to a single output Triton kernel. The outermost hl.tile loop becomes the launch grid of the kernel, and then inner loops become device loops in the code. So the most critical language construct in Helion is this hl.tile construct, which takes in a multi-dimensional size, and it subdivides the iteration space into tiles. So the exact way that the iteration space is divided into the tiles is up to the autotuner, and it often is really important to subdivide the iteration space differently on different devices to get the best performance. And so by making this tiling, the details of the tiling up to the autotuner, things like tile sizes and iteration orders, even flattening can be tuned by the autotuner. So now I'm going to go over the configuration space, and this should give you a sense, especially if you're familiar with both PyTorch and Triton, it should get you a sense of what Helion is doing. So the first type of choice that the autotuner is iterating over is iteration or indexing choices. So in Triton, there's 3 different ways to specify indexing. You can do it with pointer math, you can do it with block pointers or tensor descriptors, which are more structured ways to do it. And in Helion, indexing is done in a PyTorch style way. So you take your tensor and you index into it either with scalar values or with these tile objects that you get from the hl.tile loop in your program. And when you index into a tensor with tiles, you load an entire tile out of the underlying tensor. And what we find is that the best type of indexing often depends. Like often what we see is tensor descriptors are better for larger sizes, and pointer indexing is better for smaller sizes. And in Triton, switching between these is pretty tedious, but it can be automatically done by the Helion autotuner. The next type of choice I'm going to talk about is implicit block sizes. So in a lot of lower level languages like Triton, you need to manually manage block size information. So I've sort of highlighted all the places in sort of the equivalent Triton kernel where the block size is handled. You need to lift it to an arg. You need to do grid computations to figure out what your launch grid is. And then there's just a lot of work to manage block sizes. And this is all automated in Helion, where in Helion you just say hl.tile, and the language manages block sizes on your behalf. And one of the big advantages of having the language manage block sizes on your behalf rather than specifying them manually is we can do things like loop flattening. So there's a configuration to flatten loops, and when you do flatten loops, we take that same input source code, and instead of mapping it to 2 tile sizes, which with a square tile, we flatten the iteration space into 1 dimension and just have a 1-dimensional tile. And this gives the autotuner a lot more choice that would require program rewrites in a lower level language. The next thing I want to talk about is reduction rolling. So if you have a reduction here where you're taking a 2D tensor, you're summing up the rows, there's actually 2 different ways to do this in a lower level language like Triton. You can just do the regular load as you'd expect, but the problem there is that if your row size gets larger than what fits comfortably in an SM, then you'll either get spilling or just a failure to compile entirely. And so the other way to do it is to create an accumulator and loop over your data. And we're automating this transformation in Helion and can auto-tune between these 2 different types of choices. The next area that we're tuning over is PID types, so the program IDs in the output code. So when you're launching a program or a CUDA kernel, you have this launch grid, and you can either sort of set the launch grid size dependent on your data, or you can use a fixed size launch grid, basically launching 1 program per SM, and then iterate over sort of virtual program IDs. And these different ways are often significant rewrites to kernels, but to get the best performance, sometimes you need one, sometimes you need the other. So it's a great thing to auto-tune over. We can also change iteration orders and loop ordering. So we have you can reorder loops by specifying loop orders, and we basically just swap the dimensions of the iteration space. You can also specify more complex optimizations like L2 grouping, where we introduce subtiling in the iteration space to improve cache lethality, which is an optimization we can automate. Then there's lots of tunables in Triton that we just basically pass through to the autotuner. And while Triton exposes a lot of these knobs under the hood, most people aren't tuning these or trying to optimize these by hand. And so by exposing them to autotuner, we can automatically search over a wide space of available programs. And then finally on the settings space, we do automatic masking. So masking is something that's subtle and can be hard to get right, especially if you're not testing with non-power of 2 inputs. And so we make masking easier by automating masking choices. So next time I'm going to talk about the autotuner, and the autotuner is a really key part of the Helion language. And so the autotuner typically takes about 20 minutes to search 1,200 candidate Triton kernels. And today we have some relatively simple autotuning algorithms built into Helion. We have a pattern search, sort of nearest neighbor type search. We have a differential evolution, which is an evolutionary algorithm. But in the future, we're really excited about especially machine learning driven ways of driving the search. So we could possibly have an LLM guided search where we ask an LLM what are the next configurations we should try. And then there's other sort of machine learning driven approaches like reinforcement learning. And so I think this is an exciting area of future work to look into more sophisticated auto-tuning algorithms. But our basic auto-tuning algorithm is working pretty well in practice. And this is what we call pattern search. And so the way pattern search works is you start with an initial population of just 100 random configurations. These are taken uniformly, randomly across the search space. You then select the 5 fastest configurations. You hill climb by looking at nearest neighbors to local minimums in each of those 5 points, and then you select the fastest one. And this is a pretty good baseline algorithm. It's relatively fast, and is showing good results so far. So one thing that's a challenge in any language that uses an autotuner is deployment, because autotuning takes a long time. You don't want to be running your autotuner in your production cluster with hundreds of thousands of GPUs. And so the way to deploy a Helion program is ahead of time autotuning. You run the autotuner once in either a development or staging environment with representative inputs and representative hardware. And then you can deploy that autotune configuration to your cluster. And so the simplest way to do this, if you want to just use one configuration for all inputs, is you can just copy and paste the output of the autotuner. This is what it looks like into your program. And then at that point, we won't run the autotuner anymore. We'll just use the configuration you pasted in. For more complex setups, you might have multiple shapes you care about. So in this example, we have a small shape and we have a large shape. We run the autotuner twice, once for the small shape and once for the large shape. We save the configurations to disk. And then we add 2 configurations to the decorator of the Helion kernel. And when you specify an explicit list of configurations to the autotuner, what we do is whenever we see a unique input shape, we try them both, and we pick whichever is fastest. And so this is a very cheap algorithm because you only need to run compile twice and run twice. But it gives you a case where if you need different configs for different sizes, you can get good performance for both. And then for even more advanced users, you can do manual routing. So I've done an example here where I flip static shapes to false, so you get a single kernel that can work for lots of sizes. And then I ahead of time compile the small kernel and the large kernel that we generated in the previous slide. And then you can write your own custom routing function. And this custom routing function basically says if the numL is small, then use one function. Otherwise, use the other one, and this allows you to skip that small like run the 2 and pick the fastest one step. You can just have the kernels ready without any runtime tuning at all. And then the last thing I'll mention on the autotuner section is this register tunable flag. And so we have this powerful autotuner that allows you to search over lots of configuration spaces. Most of the configuration spaces that we're searching over are implicit, where you write hl.tile in your program. That implies lots of choices around how your program is tiled. But sometimes there's choices that are part of the algorithm, where maybe there's 2 different algorithms you use. Maybe you want to do a split K versus not a split K. And so for these types of things, you can register a custom tunable. You describe what that type of tunable that is. Is it an enum? Is it an integer, etc. And then the autotuner will be tuning these user-defined parameters simultaneously with the ones that are implicit in the language. So now I'm going to talk about performance. So for performance, I'm going to first walk through 3 different case studies, and then I'm going to show some sort of wider performance numbers that span across a large number of benchmarks. So this is comparing attention performance on an NVIDIA B200 that's downclocked to 700 watts. And we have 3 different versions of Helion here. We have Helion combined with stock Triton. We have Helion combined with the Facebook experimental branch of Triton, where we've implemented a better warp specialization algorithm. And then we have that combined with advanced compiler configurations, which are more complex settings for PTX-AS that get better performance. And as a baseline, we're comparing this to PyTorch eager mode, a bunch of different versions in Triton, so flex attention, and the tutorial version of Triton. Then we're also comparing this to Gluon and cuDNN. And we can see here that Helion has roughly similar performance to Gluon, but there's still a small gap to the performance of cuDNN. So this next case study, I'm going to compare to TileLang. This is on the Mamba 2 chunk scan kernel, which they presented in their paper. And here we can see that Helion is outperforming TileLang on all the shapes that were chosen in their comparisons. And then for the third case study, this is a comparison to Qt DSL, and this is a kernel from the Quack library, which is a library of Qt DSL kernels for RMS norm backwards. And we're comparing to eager, Triton, and Torch compile. And we can see here that Torch compile is pretty good on the smaller input sizes. Quack is pretty good on the larger input sizes. But Helion and also the fused Triton, which is sort of equivalent to the Triton code that Helion is generating, are both giving robust performance across all sizes. So here we're sort of zooming out one level, and we're now looking at lots of different kernels. And for all of these kernels, we're showing we've run each kernel on a number of different sizes. We've taken the geonin speedup over PyTorch eager mode. So 1x means running the same speed as PyTorch eager, and higher is better. We can see that across most benchmarks, Helion is outperforming both Torch compile and handwritten Triton. Even though that Helion is generating Triton, we're still able to very consistently beat handwritten Triton code. And the reason for this is our search space is larger. So when a human is optimizing handwritten Triton code, they might try 10 different ways of writing their program if they're very persistent, while Helion is trying thousands of ways of rewriting that same Triton program, and that larger search space means that very often Helion is able to find better, more optimal ways of writing the kernel. So this is the same type of numbers, but now on an MI350 for X from AMD. And we see a very similar story. And this really highlights the performance portability of Helion, because often when you're switching between hardware types, you end up needing to make changes to your Triton kernel in order to get the best performance. But the autotuner is able to squeeze more performance out automatically through tuning. So Helion also works on other hardware. So I've mentioned NVIDIA and AMD results. Helion also works on Intel XPUs and MTIA, which is Meta's custom accelerator. One big advantage of Helion mapping to Triton is any hardware which has a Triton backend works well with Helion just out of the box. But over time, especially to get the best performance, it's important to add knobs, because every hardware has some hardware-specific knobs that sort of represent those hardware abstractions. And it's important for the autotuner to be able to tune over those knobs that are important for each hardware. And so as while the first step of just getting things running is pretty easy, it's always important to take that sort of second step, which is to expose knobs in the autotuner so that we can get the best performance robustly. So getting close to the end, I have one slide to sort of talk about the internals, about how the Helion compiler works. Helion is a Python embedded DSL. And so we start with a Python AST. We then annotate that Python AST with types and metadata. We then convert this AST into an FX graph, one FX graph per basic block. And every node in this FX graph that we create is annotated with the corresponding inductor IR. So Torch inductor is the compiler that backs Torch compile by default. And Helion reuses large parts of torch inductor in order to map PyTorch operations into the output Triton code. And so doing this without torch inductor would have been really challenging because PyTorch is a lot of operators, more than 2,000. Having a robust base compiler that can do this, that can handle all those PyTorch operations, allows the Helion language to basically include most PyTorch operations as legal operations in the language. So we have this IR, we do a bunch of compiler passes on this IR, then finally we do codegen. The codegen incorporates the configuration, and so we only use the configuration during codegen, so basically everything on the left of this can be cached and is just run once, while things on the right are run once per autotuning instance. And then we also take the host code, which is just standard PyTorch code, and for that we just do an AST rewrite. So we take the loop that's in your Helion kernel, we replace it with a function call, and then we generate that as output. And so with that, I'll take questions. Helion is out in beta now. We'd love for you to try it. We'd love to have some feedback and bug reports, which really help shape the language. And if you want to connect with us, we have a channel on the GPU Mode Discord, and we're also running a webinar Q&A in December. Yeah, any questions?
Okay, thank you for your presentation. You mentioned that we can add new backends other than Triton, for example, like Mojo or Qtile or like CUDA or anything else. But I wonder if we have any requirements for those backends to be compatible with Helion's autotuning mechanism. So is there any requirements for like new backends if you can add them?
Yeah, so it would definitely be possible to add other types of backends for it. If you want to support sort of custom hardware, there's a few different ways to do it. One is you could add a Triton backend for your custom hardware. We've seen that work for now, I think, more than 10 different types of hardware that work with Triton. And so really, Triton has sort of become sort of the common language that spans across a wide variety of different accelerators. If you want to put in additional work, you could add a non-Triton backend to Torch Inductor. Torch Inductor already has 5 different backend languages at this point. And then after you've added your custom language as a backend to Torch Inductor, you could then extend Helion to support that custom language as well. There's a few of those that people are exploring, but currently all the backends are Triton-based.
I guess thanks for the talk. Just can you provide some details on the Triton comparison? So you had some pretty good numbers where you're getting 10x speed up. What is the human missing? And then secondly, like who are actually, where'd you get those kernels from? Like, is that from your production GPU team or?
Yes, so most of the baseline Triton kernels were taken from Liger, which is an open source kernel library that's used in a number of places. So these were basically like taken, these were real kernels from the wild. A few of them were taken from other places. I'd say like 80% of them were from Liger. Basically like what the user's missing depends on the kernel. Like in some cases, they got the block sizes wrong. In some cases, you needed to do a persistent kernel. In some cases, you needed to add cache eviction annotations, and the user didn't do that. In some cases, you needed to add the loop unrolling flag to tl.range. And so just like sort of what the user missed is sort of different for every kernel, but we're able to consistently beat handwritten Triton just because we're searching such a larger search space.
So I have a question. So basically, we see that Helion shows very good performance, but in some cases in the table, Torch compile still beats the Helion, right? In these cases, do you know why and what's missing from the Helion side?
Yeah, so in some of those cases, Torch compile includes optimizations in the the code that the Helion kernel doesn't have. And so Helion is tuning over sort of structural, like how to schedule an algorithm, but in some cases you need different algorithms. In some cases, the Helion autotuner just missed, and so because it's a stochastic auto-tuning process, sometimes it doesn't find the global optimum, and so in those cases we need to improve the autotuner. But in most cases we're seeing when we are a little bit worse than torch compile, we're usually pretty close. So in some cases it's also just random noise.
Hey, Jason, this is super cool. I'm down here in the middle. This is super cool. How does it deal with TMAs and other things that Triton isn't always great at? Is there hooks into that? You say the expose more hardware details up?
Yes. So in Triton, you need to explicitly do TMAs, which is really annoying because, especially for hardware that doesn't support TMAs, your kernel ends up not being portable at that point. And so because we're doing indexing sort of with PyTorch style indexing, where we have rich tensors and we are, you're trying to load a tile of that tensor, it's a lot easier for us to automatically generate TMAs. There's a bunch of cases where like TMAs have weird restrictions, like this thing must be greater than 16 or this thing must be a multiple of 8. And we have a bunch of passes that basically just check for that and disable TMAs if they're not there. I think we have like 1 or 2 cases where we're doing like code rewrites to try to like shoehorn stuff that like TMAs don't want to support and force them to support it by like introducing a join or a split. And that's something that can be sort of tedious and probably troublesome, but hopefully the Helion language is automating most of that for the user.
Yeah, right here.
I'll take this is the last one. I think they're giving me the 0 minutes question, but go for it.
I want to ask really quickly. Thanks for the talk. A lot of the knobs that you like expose and then the config specifies and you auto tune over, like they're global, right? So they're like once per kernel. What if you have multiple loops that you want to like control how they're unrolled, or like multiple loads that some might use block pointers and some shouldn't? Like, have you found that to ever be an issue, that you would want to specialize into different ways for a single knob? And do you envision any good abstraction interface to let people do that?
Yeah, so most of the configurations that I talked about are lists. So if you have multiple loops, you'll end up getting different configuration flags for every loop, and so the autotuner can decide to do different stuff on each loop. There's a few ones like tensor descriptors where they're just one flag because we haven't seen cases where there's really a big need to mix them. But if we find those cases, we can change them to lists. But for the most part, like if you have 10 loads in your program, you're going to get 10 cache eviction policies exposed to the autotuner, and the autotuner can independently set them all as well. All right, thank you so much.